Hey everybody, we are back. We're going to keep plugging forward with Chapter 9. We went over a few different reactions of alcohols the other day, so we're going to keep on rolling with that. There's one major category left, and this is dealing with a particular type of species called tosylates. Stylus is being especially tricky today, so bear with me. Okay. Tosylates. Just like with anything else we've seen so far, tosylates are going to be basically a mode, a way for us to turn a bad leaving group into a good one, right? So, if you know that an alcohol has an OH group, right? We're going to be transforming it into something else. A tosylate is going to look like this. And this is an abbreviation. ROTS, or ROTS for short. I never really realized that before, but that's kind of funny. The TS stands for tosyl, all right? Here's the reason we abbreviate this. If we wanted to expand this out, this is really what it looks like. This right here is the TS part. So you can kind of see why we wouldn't want to have to draw that every time, right? So that combined with the RO, that's your tosylate, all right? This is referred to as a tosyl group. Jeez. I'll have to get a new stylus. This one is conking out on me. All right. Okay, so how do we do this? Well, and first of all, why do we do it? Well, we do it because, just like we've seen with several other examples, tosylates have good leaving groups. All right. They just happen to be pretty versatile, so that's kind of why they get their own focus here. First of all, let's talk about how you make a tosylate. All right. So it starts off with an alcohol. All right. And an alcohol is going to react with a compound called tosyl chloride. And I'm going to draw the expanded structure down here just so you can see it. This is the source of our tosyl group. All right, and that sulfur has a Cl on it. Now, again, we don't want to draw this every time, so we frequently just abbreviate this as TSCl, tosyl chloride. All right, so we can react an alcohol with tosyl chloride in the presence of pyridine. We've seen pyridine a couple of times already. It's going to function as a weak base, just like it did the other times. So basically what happens here is, whoops, decline that, so hopefully she doesn't get mad at me. I want to draw this with a bond in it. All right, so basically what happens here is that the alcohol group will attack the sulfur in your tosyl chloride. Your Cl minus will leave. To give you this. And then the pyridine acts as a weak base, deprotonates that oxygen, and voila, you've got your tosylate. By the way, if this looks a little messier, my stylus is totally kaput. It's not working, so I'm having to use my finger. So, having to ad-lib a little bit, but it should work out all right. All right. So that's how you make a tosylate. Pretty simple. Basically, just a direct reaction there. All right. What type of reaction is that? Synthesis of tosylates proceeds via an SN2 reaction on its own. Right. We're using the alcohol as the nucleophile, and the sulfur is being attacked. All right. This works only with primary and secondary alcohols. Can't really do this very well with tertiaries. Why? 2 words, steric hindrance, right? Tertiary alcohols would be just too big to really effectively attack and get close to that sulfur, so this really only works well with primary and secondary alcohols. One interesting thing to keep in mind is that sometimes you're going to be working with an alcohol that has a stereogenic center, all right? This is going to be the hardest thing to do with my finger, I think. Oh, that's not too bad. Okay, so let's say we have something like this. And you're making a tosylate. Now, just like we saw before, we're going to get a nucleophilic attack on the sulfur, and that's going to get kicked off. Pyridine's going to deprotonate. I'm just going to sort of skip ahead to the end here because it follows the same mechanism that we saw before. Let's see if we can predict the stereochemistry in the product. All right, because we know this is an SN2 reaction, and you guys might have it in your heads from one of the previous chapters that when you have an SN2 reaction, you always get complete inversion, right? Keep in mind, though, that is only when the carbon being attacked turns out to be stereogenic. This one's a little different, right? In this case, the stereogenic carbon contains the attacking species, the OH, right? So since the stereogenic carbon is not attacked, you actually retain your configuration. All right, so that's something to remember. Whenever you're synthesizing a tosylate, you're going to retain whatever configuration that you had before. There's not going to be any inversion. There's not going to be any racemic mixes. You're always going to retain. Okay? All right. So, that's how you make tosylates. Pretty simple. Now, what do you do with them? As it turns out, tosylates are fairly versatile. There's a couple of different things that you can do with them. Once you actually make a tosylate, they can undergo SN2. Here, I'll write this in a more detailed fashion. Tosylates can undergo SN2 or E2 reactions depending on the conditions, right? Depending on the circumstances. All right. Let me give you a few scenarios here. All right. Let's say you have a primary tosylate. A primary tosylate is when you have the tosyl group attached to a primary carbon. If you have a primary tosylate with something that can act as a strong nucleophile. This is really awkward writing with my finger, by the way. That is going to give you an SN2 reaction. All right. Primary tosylate, strong nucleophile, gives you an SN2 reaction. If you have a primary or secondary tosylate and something that can act as a strong base, but a non-nucleophile. And do you remember an example of that? Right? The example we always go to in those situations is tert butoxide. If you remember, tert butoxide looks like this. Right? Really strong base, but it's too big and crowded to be a good nucleophile. In that case, you're always going to get E2. And then the third situation, if you have a secondary tosylate, and something that can act as both a strong base and strong nucleophile, that's when you get the dreaded mixture of products. That's when you can get both of them. Okay? So in summary, if you have a primary tosylate, as long as you have something that's not big and sterically hindered, it's going to go SN2. All right? However, if you have a primary or secondary with something that's both a strong base and a non-nucleophile, like tert butoxide, it's going to go E2. If you have a secondary tosylate and you have something that can act as a strong base or nucleophile, it'll do both of them. Let me show you some examples here. I'm going to try my stylus again. Let's see if this is working now. I'm cautiously optimistic. We'll see. Okay. Let's say we had this. Well, maybe I'm not as optimistic. Alright, so we have a tosylate, and we're going to react it with tert butoxide in the presence of DMSO. Alright, so if we look at this, it looks like we have a secondary tosylate. Oh my goodness, I can hear my dogs barking. Sorry about that. We have a secondary tosylate here. And if we look over here, we have tert butoxide, which we've seen can be both a strong base, or excuse me, which we've seen can be strongly basic, but highly sterically hindered, so it cannot act as a nucleophile. That means we have to have an E2 reaction and an E2 reaction only. So what you would do is just like we've done in the past. Look for beta hydrogens, right? So you're going to lose the tosyl group, and you're going to lose the beta hydrogen. So one beta hydrogen's on the end here, so you could form a double bond between these two carbons. You also have beta hydrogens on this carbon, so you could form the double bond there, right? Those are all the beta hydrogens that you have, but notice that here, well, come on, there we go. We have a trans product, so you have to account for the fact that we can have, I'm going to have to use my finger. The struggle is real, guys. Alright, but you always also get the cis. So, in this case, it's entirely E2. You get 3 different products, all of them elimination products, alkenes. Alright? Now let's try this one. Wow, what a horrible looking pentagon. I am so ashamed of myself. That's a little bit better. Alright, let's take a look at this. Now, this is a primary tosylate, right? That tosyl group is attached to a primary carbon. Alright, we're going to add NaOCH3 in the presence of acetone. Alright, so this is going to serve, really, the purpose of giving us OCH3 minus. And, hopefully you can recognize the OCH3 minus is both a strong base and a strong nucleophile, right? However, if you have a primary tosylate, it's going to definitely have more of a tendency to react as a nucleophile if it can, right? That's what primary tosylates do. Primary tosylates prefer SN2 over E2 if they have a choice, for lack of a better expression, right? So that's what's going to happen. That OCH3 is not going to act as a base. It's going to act as a nucleophile, knock off your tosyl group, and you're going to get a substitution. And you're going to get a substitution only. No competing eliminations here with a primary tosylate. Okay? All right, let's try one more. All right, let's try a tosylate with the same species we did in the last reaction, NaOCH3. So this one's kind of similar, except for the fact we have a secondary tosylate, right? Not a primary. All right, so you have a secondary tosylate. You have NaOCH3, so OCH3 minus. It's both a strong base and a strong nucleophile. We learned that if you have a secondary tosylate, that means you can actually have both, and you will have both, right? So you are going to get the substitution, right, the SN2, but you're also going to get elimination as well. You're also going to get E2. So just like before, look for the beta hydrogens. And be sure to look for any stereoisomers that you can draw. So this one will give you 4 different products. All right. Okay. All right. I'm debating whether I want to stop here. No, actually, I'm going to keep going. You guys were hoping I was going to stop. Poor students. All right. That is all the reactions for alcohols for the moment, though. All right. So now we want to look at ethers. Now, the good news is ethers don't do as much as alcohols. In fact, really, they only react with one type of species. However, they do it in a couple of different ways. All right. So what we're going to look at is going to be reactions of ethers with strong halogen acids. That's going to be HX. So that's going to be, for our purposes, either HCl, that's going to be, for our purposes, either HBr or HI. Okay? So let's take a look. Basically, here's how it goes. Remember that an ether looks something like this. You have this COC, or ROR linkage. Basically what happens is you're going to add your halogen acid, and you're going to add 2 equivalents. We've seen this before when adding base to dihalides to make alkynes, right? It basically means we add enough to react 2 times. And what's going to happen is each one of these R groups ends up halogenated. So you end up producing this, and this is your main organic product. So you also get water as a byproduct. Okay? So you see, basically what we do is we use HX and it sort of cuts apart this ether. It sort of cleaves it, all right? And it does this in a couple of different mechanisms depending on what type of ether you have. So let's take a look at a couple of patterns here. All right, for ether cleavage, here's when we get an SN2 reaction. If both your R groups are primary. All right? If both those R groups are primary, then you're going to get an SN2 mechanism. Sorry, I'm having to write this bottom one up here. Kind of looks weird, but I think you guys will get the message. When do we get an SN1 mechanism? You get an SN1 mechanism if either R group is secondary or tertiary. Kind of weird, huh? Don't you wish they could just, all do the same thing? Well, I do too. It'd be a nice little land of sunshine and rainbows if it did, but it doesn't. So we're going to take a look at some examples here in which we can figure out, where we're going to have an SN1 or we're going to have an SN2 reaction. Okay. All right, let's take a look at something like this. This is diethyl ether, right? Symmetrical ether, got two ethyl groups on it. All right, so we're going to set that up to react with HI. All right, now, just like with alcohols, one thing we got to do here is we have to turn a bad leaving group into a good leaving group. Your leaving group essentially here is O plus one of the alkyl groups, right? That would be an alkoxide. Alkoxides are horrible, horrible leaving groups, even worse than hydroxide. So you got to turn it into something good. Just like before when we protonated OH to make water, what we're going to do is we're going to protonate this oxygen with your hydrogen. And basically what that's going to do is that's going to turn our leaving group into an alcohol. Alcohols are excellent leaving groups. All right, so we have this, and we also have I- left over, lurking in the background. That can act as a nucleophile, and it can attack one of the carbons adjacent to your oxygen. In this case, it doesn't matter which one you pick because you get the same thing either way. All right, so I is going to attack, and the alcohol group acts as your leaving group. And that gives you this alkyl halide, this alkyl iodide. However, that's not the only thing. You see, you get another product here. You get an alcohol, right? Here's the tricky part. We've seen this before. You have an alcohol and you have a halogen acid. That can produce a reaction. All right, so you're out. That's why we add two equivalents of HI. One of them to cause cleavage of the ether, and then the other one actually reacts with the alcohol. So you have another HI that comes in. It protonates your alcohol. And then that other I- that's left over will come in, attack that carbon, kick off water, and it produces another molecule of your alkyl iodide. In this case, you end up with two identical alkyl iodides and water. Okay? So basically two stages this. First is the cleavage of the ether, and then the reaction of the alcohol byproduct. So you're always going to get two molecules of alkyl halide. Sometimes they're the same, like in this one. if you had an unsymmetrical ether, something like this, you'd end up with two different ones. You guys can go over the mechanism on your own. I'm just going to go ahead and write the products here. Remember, each, whoops, not an OH, each R group turns into an alkyl halide, so these would be your organic products here. Okay? Alright, so those are examples of when you get SN2 reactions. Now, if we had something like this, though, let's say we had tert-butyl methyl ether. Alright, and let's just use HBr. Okay, so this is going to start off the same way as the last time, right? We got to turn a bad leaving group into a good one, so we're going to protonate the oxygen. Oh, I hear my wife is home. Hope she's not mad at me for not answering her call. If I get in trouble, please send help. Alright, this is a little bit different, because what can happen here is, since we have a tertiary carbon attached to that oxygen, this alcohol group, it can just go ahead and leave. And it produces a carbocation. Alright, this is your SN1 mechanism. Alright, we have a tertiary carbocation, very stable. That Br minus can attack it, and that produces this product, right? And then, again, just like we saw last time, we have an alcohol byproduct that can be worked up and also ends up producing an alkyl halide. So, similar products in this case, but it proceeds via an SN1 mechanism. All right? So you may think, okay, well, it didn't really end up changing the product any, so does it really matter? Well, yes, indeed it does. Let's take a look at this one. Okay. All right, so we have a secondary ether. We have an ether with a secondary R group on it. We're going to protonate it, blah, blah, blah. Okay. All right, so we said if we have a secondary or tertiary, it's going to go SN1, so following that logic, that means we're going to lose that alcohol. Right? And we have a carbocation. All right, and this is a secondary carbocation. However, don't ever forget what we learned last time. We always have to look for carbocation rearrangements if we have secondary carbocations. We didn't have to worry about that last time since we had a tertiary. We can have a rearrangement here. We can have a 1,2 alkyl shift to produce this. Tricky, tricky, right? And that's not something you necessarily could have predicted unless you actually went through the mechanism. Then and only then does your Br minus attack, and you end up getting this particular alkyl bromide. And then, of course, the alcohol gets treated like it always does. And you get the other alkyl bromide as well. Very good. And that's basically it for ethers. Like I said, they don't really do much. They only have this one major type of reaction. It just can happen in a couple of different ways. All right, I'm going to cut the video off now. We have one other major group of reactions, or compounds to look at as far as reactions. That's going to be epoxides. All right, so until then, I will talk to you later. Bye-bye.